Good afternoon. Welcome to today's class. And today I want us to discuss something on power factor. And this one is specifically for the TVET CDAC students and any other person interested in having knowledge to do with power factor. And our topics today we'll have a brief introduction. We'll look at the terms associated with power factor. We'll discuss the power triangle. We'll look at methods of power factor correction, the advantages and disadvantage of each method. Then later at the end we'll look at the numerical calculations involving power factor. So let's begin. Welcome. So we know that electrical energy is exclusively generated. So after you've done the generation, the next stage you do the transmission. Then after you've done your transmission, there is what we refer to as the distribution channels and the networks. And all those stages are done exclusively for an AC power, that is AC current. And to make it clear, power factor is mainly associated with alternating currents. So the process of generating, transmitting and distributing to the final consumer can be simply summarized by this flowchart. It's a flowchart. You can talk of it being a flowchart or a figurative block diagram, whereby we have the power plant, and it is at the power plant where we do power generation. Then from that power plant, after generating, you receive or you obtain an alternating current. Then that alternating current is injected to a transmission transformer. The transmission transformer is purposely for increasing the voltage level and reducing the amount of current. So that one, after it has passed the transformer, it enters the transmission lines, and in this transmission line they operate at a very high voltage with very little current. And this is the reason why voltage is high with a very small amount of current is to minimize the line losses, due to the reason that our transmission channels are mainly made of aluminium, and in most cases there is copper. So we are trying to minimize the power loss along the transmission lines. Then once the transmission channel comes to an end, there is a distribution transformer, and this distribution transformer is mainly found at near the consumer's point or near the power consumers. And in all that process it brings about a crucial concept of power factor. So what we have on this side, it's also similar to this, but you can see these are just 3 blocks: from generation, transmission and the distribution network for local consumption or industrial consumption. Then now this one is a diagram, and This explains what I was explaining earlier. So we have our power plant here. This power plant, we have our power plant. Then we have our transmission transformer at this part. It is from this transmission transformer now we are able to obtain our transmitting voltage. As per this diagram is 400 kilovolts at a very small current, and these are transmission towers. This is also another transmission towers, and from this tower to this tower we have a connecting cable, and we are saying that it is a high voltage transmission line. Then we have a step down transformer here, and in most cases it is referred to as a substation. Now in a transmission line you may have several substations depending on the customer's choice. That is, we may have a substation whereby it is operating as 66 kilovolts, and that is mainly for heavy industries, 33 for medium industries, and 11 kilovolts for light industries, and also for consumers. So from this part it forms the local distribution networks. These are the local distribution networks, and if you look keenly at this post, we have another step down transformer, and this step down transformer is stepping down to 240 volts for this home. So this one is a client, and the client requires a voltage of 240 volts. This is enough. Same is explained to here. The entire process on our left side is similar to what we have on our right side, but on our right side this one is more figurative. It is more figurative, and we have our initial source of energy here being cool, and that's why you see the generating station is producing some smoke. Then the reason why power factor is important, you find that in most cases our loads are inductive in nature. So for them being inductive in nature, it means they consume a very low lagging power factor. So they consume a lagging current, and that lagging current operates at a very low EF. And in that case we have loads such as the induction motors, the arc lamps, sometimes the fluorescent lamps, etc. Now low power factor is highly undesirable. It is not desired, it is highly undesirable, since it causes an increase in current which results to additional losses of active power. So once you have a very low power factor, it means you have to operate your loads at a very high current, and when your loads are being operated at a very high current, it means you will incur high power losses. You will incur high power losses in the elements of power systems, from generating station down to the utilization devices. So with me here is just a figurative example of an induction motors. So on this side is a single phase, induction motor, and on this other part is a 3-phase induction motor. The way it looks inside, the arrangement of the rotor, the stator windings, and all the crucial elements. So this is just an example for reinforcing why we need power, why we need a high power factor, and why we need to be very considerate when it comes to power factor. So it is important to maintain a PF close to unit as possible. High power factor ensures the following. One, it reduces energy cost, and this is by the fact that less energy is wasted, which implies you will incur very low bills if you maintain your power factor being as high as possible to an approximate value of a unity. There is improved system efficiency, and this enhances the overall performance of the power supply. So you find that when your system is operating at a very high power factor, the overall efficiency is improved, and that ensures that your supply is maintained steady. So then we have terms that are used in power factor, or you can say these are common wordings that whenever you're interacting with power factor, you will not miss them. So the first one is the power factor itself, and this is simply the measure of how effective electrical power is being converted into useful work. How effective is that power being converted into a useful work? Then you can also define power factor as the ratio of real power, or the active power, measured in watts to apparent power measured in volts amperes for an AC electrical circuit. And as I said, power factor is mainly associated with alternating current circuits. We can also define the term power factor as the cosine angle, the cosine of the angle between voltage and current in an AC circuit. So power factor can be expressed mathematically as the ratio between real power measured in watts divided by the apparent power measured in volts amperes. Then the other term is we have the real power. So simply when we hear the word real power, it simply refers to the active power, and in simple words, it is the actual power consumed by the load when that load is performing useful work. It is measured in watts. It can also be measured in kilowatts. It can also be measured in megawatts. It can also be measured in megawatts and gigawatts. Then the other term that is very common is the reactive power in an AC circuit, and this one is simply the power that oscillates between the source and the load, or simply the power that flows back and forth. It flows back and forth inside the circuit, and this power is necessary for creating magnetic fields which are necessary for inductive loads. It is measured in volts amperes reactive. The var, that is volts amperes reactive, kVAR. It can also be measured in a bigger unit, that is the kilowatt amperes reactive, kVAR. Then the other term is the apparent power. And apparent power, it is simply the composition. So this is simply a combination of real power. It is a combination of real power and active power. So that simply tells you that apparent power in an AC circuit, it has two components. That is the component of the useful power, that is the active or the real power, and the non-useful power. Then you can also say it represents the total power flowing in the circuit. It is measured by volts ampere of the kilovolts ampere, kVAs, and this one is abbreviated by capital letter S. It is capital letter S in a circuit. Then the other term is the lagging power factor. Lagging power factor, and this one occurs when the phase current lags behind the voltage of that phase. So you can simply say it occurs when the current lags behind voltage, and it is commonly experienced in inductive loads, e.g. the motors, induction motors, and the transformers. Then we have the other term as the leading power factor, and this one occurs when the current leads voltage. Or you can also say it occurs when voltage lags behind the current. When voltage lags behind the current, we say that we are experiencing a leading power factor, and it is commonly in capacitive loads, such as the capacitor banks that are used to improve power factor. And with me here is just a figurative example. If you can see, in these two waveforms, we have the voltage here, and the voltage is behind our current. So that means current is leading the voltage. Current is leading the voltage, and it is leading by an angle phi. The angle phi. Then so in that case, we say that our PF is lagging power factor. Our circuit is experiencing a lagging power factor, and on the other side, we have voltage being behind current. So in this case, we can say that current is leading the voltage, and it is leading by 90 degrees, and in that case we say that our circuit is experiencing a leading power factor. And we have said an example is a capacitor bank, or a capacitive load, and this one, the lagging power factor, is experienced in inductive loads. Then the other term is a unit power factor, and we simply say that this is a power factor close to a unit. In terms of percentage, it is a power factor which is 100%, and it simply indicates that all the power supplied is being utilized effectively. So at a unit power factor, it implies that all the power supplied from the source is utilized effectively by that load to perform the useful work. And this is a good demonstration of a unit power factor, whereby if you look between the voltage and the current, we say that the current is in phase with the voltage. So that means if you visualize the two, it is like there's no difference in terms of the tilt angle. So they are at this, when we at unit power factor, we'd say that the angle is equals to 0. So that means there is no difference in phase because the angle is equals to 0. So both the voltage and the current are moving along the same path. They are traveling along the same path with no difference in terms of the angle. So a unit power factor implies that the load's apparent power, and we said that the apparent power is the combination of real power and reactive power. So it simply implies the load's apparent power is equivalent to the real power. So therefore it implies that there is no reactive power. There is no wastage of power that is rotating or oscillating from the source to the load. So all the power is being consumed, and that's why we are saying that the load apparent power is equals to the real power. Then again, at a unit power factor, we say it is equivalent to 1, and that implies the angle between the current and voltage is equivalent to 0. So at a unit power factor, the angle between the phase angle between current and voltage is equivalent to 0 degrees. Then at a unit power factor, the load assimilates a pure resistive load. So it simply implies that the load behaves like a pure resistor. It is a pure resistive load. Then the load current and voltage are in phase. That is what I was explaining here. They are moving at the same pace without any changes in the angle. The phase angle is equivalent to 0. Then the other term is power factor correction. Power factor correction, these are simply the techniques or the devices used to improve power factor by reducing the amount of reactive power. So in short, we improve power factor by reducing the amount of lagging reactive power within that load, and this one is best achieved by use of capacitors, and this is the reason. The capacitors take leading current which neutralizes the lagging reactive power either partially or completely. If it is able to do it completely, then we say the power factor is unit. Then the other term is the harmonics, and harmonics are simply disturbances. They are distortions or disturbances in electrical waveforms, and they can affect the power factor. They can affect the power factor and the overall system efficiencies. Anyway, in simple language, you can say these are instabilities in power supply. Then we have the load factor. The load factor is simply the ratio of average load over a period to the maximum load during that period, indicating the efficiency of load usage. So therefore, we can say that PF is the cosine of angle between voltage and current in an AC circuit. So that simply means it is the cosine of the phase difference. The cosine of the phase difference. And the phase difference is what will be represented by phi. It is represented by phi. Then for a sinusoidal waveform, and a sinusoidal waveform takes this form. A sinusoidal waveform has the positive and the negative part. It has the positive and the negative part. So this is what we refer to as a sinusoidal waveform. We say that for a sinusoidal waveform, PF is the cosine of the phase angle between voltage and current. So therefore, power factor is equals to cos phi. So cos phi is a value in degrees. So, and therefore cos phi, you can say that cos phi is equals to power divided by, now this is simply the power in that circuit. You divide by voltage multiplied by current, and again this voltage multiplied by current is what we refer to as the apparent power. This is the apparent power in that circuit, and therefore if you make P the subject, that's simply multiply both sides by VI. So multiply this side by VI, and this other side by VI, and you realize that the VI on this side will cancel out, and your formula now becomes power is equivalent to, now this power you're having on this side, this is the actual power, or the true power, active power. So this is the active power of an AC circuit, and from this power we can be able to get our current I by simply saying I is equivalent to, I will be equivalent to the actual power divided by V cosine of theta, and that is simply what we have in here. That making I the subject, we get I equals to, I stands for current, is equals to power divided by V cosine of theta. So therefore, if the circuit is inductive, current lags behind the voltage, and the power factor is a lagging PF. Whereas for a capacitive circuit, current lags behind voltage, current leads the voltage, and the PF is said to be a leading power factor. So inductive circuits, they experience lagging power factor. For capacitive circuit, they experience a leading power factor because current leads the voltage. Or in other words, you can say voltage lags behind current. So consider the figure alongside. So from this figure, we can see we have I cos phi, and we have the angle between we have current, then we have current multiplied by sine of phi. So from this figure, we can actually resolve it in two components, and the first component is I cos phi. That is with voltage, and this is what if you input voltage here V and another voltage here V and another voltage here V to be VI, it simply means that the first one that is on top, that is along O to A is simply the active or the wattful component. Now this is the actual power that does the actual work in a circuit. Then again, this side we have the wattless component or the reactive component, and this is the power that simply loiters within the circuit. It flows back and forth in the circuit. It has no use, it is useless power. In other words, it is wattless component, so that means it has no any use in a circuit. And this component of current flows at right angle, that is 90 degrees with the active current. So it is at 90 degrees, and this is actually 90 degrees at this point. So you can simply say the useful current or the active current and the useless current, they are both mutually at right angle, that is at 90 degrees. So reactive component is the measure of power factor. The reactive component is simply the measure of power factor. So it is worth to note that when dealing with numerical values of power factor, always attach the wordings lagging or leading power factor. So it is lagging for inductive circuits or loads, it is leading for capacitive circuits. So in case the circuit has a power factor of 0.5 and the current lags the voltage, use or express it as a PF of 0.5 lagging PF. And again, power factor can be expressed in form of percentage. You can express power factor in form of a percentage, and that simply tells you if you have a power factor which is maybe 0.7 in form of a percentage, that is 0.7 leading in form of a percentage out of 100, you can simply say that is 70% leading power factor. So those two things are worth to note when dealing with the power factor. Kindly let us know, is it leading or is it lagging? Then there is no arm if you express it as a percentage. So let's look at the power triangle, and in this you consider the figure that is alongside, and again this figure is similar to what we had earlier. So a keen evaluation on this figure, you realize that we have real power here. So this is our real power P, and this is our apparent power S, and this is our reactive power Q. So from this figure we can see that from point O to A is represented by V multiplied by I multiplied by cos phi, and that is automatically the real power or the actual power in watts. Then we have our OB. We have from point O downwards to B, and this is our apparent power. It is a composition of the real and the reactive power. Then we have point A to B. It is the reactive power. This is our reactive power, abbreviated by capital letter Q. Then from there, our component, that is the component of this component of apparent power, that is O to B. If you take the square of OB, then you see it is equivalent to the square of O to A plus the square of A to B. So OB squared is equivalent to OA squared plus AB squared, and this is simply by use of the Pythagoras theorem. So therefore it is, in other words, saying apparent power squared is equivalent to active power squared plus the reactive power squared. And in terms of the unit, we say this is kVA squared plus kW, that is kilowatt squared plus kilovolts ampere reactance squared. Then something else that you should note, that is the lagging reactive power. The lagging reactive power is simply responsible for the low power factor. It is simply, it takes the responsibility, or it is the one that causes low power factor. So therefore you can say that the reactive component, the kVAR is equivalent to apparent power multiplied by sine of phi, and this one simply is equivalent to the actual power in kilowatts divided by cos phi multiplied by sine phi. And actually this one can be termed as sine over cos gives tangent, and therefore we can say this is equivalent to the true power multiplied by tangent of theta. Yeah, that is to say the reactive component is equivalent to the true power multiplied by tangent of theta. Now again, from the diagram that we have in, it's simply summarizing the initial slide or the initial discussion. But there are some things I would like to emphasize more here, that for a leading current, the power triangle becomes reverse, and this provides a key. It provides a key for power factor improvement, and the key is in this form. If you have a device that is taking leading reactive power, e.g. a capacitor, and you connect it in parallel with the load, then the lagging reactive power of the load will be partially neutralized, and that improves the power factor of the load. So I've said for a leading current, the power triangle becomes reversed, and that simply implies that it gives an opportunity to improve the power factor, and that power factor can be improved by connecting a device in parallel, and that device must be taking a leading reactive power. An example is a capacitor connected in parallel with the load. Then the lagging reactive component. Remember, we have said that the lagging reactive component is responsible for causing low power factor. So that lagging reactive power of that load will now be partially neutralized or completely neutralized, and in that case we say that the power factor of that load is improving. And therefore, from the same diagram, we can define power factor as, first we can define it as cosine, which is equivalent to the circuit resistance divided by the circuit impedance. We can also define it in terms of true power and apparent power, the ratio of true power to apparent power. And we can also define it in terms of PF is equivalent to cos phi, and this cos phi, we have said cos phi is the phi is the angle between voltage and current. So you take the cosine of the phase angle between voltage and current. And again, I have said we can define power factor in terms of the circuit resistance into the ratio of circuit resistance to the total circuit impedance. And lastly, you can define power factor in terms of the true power or the active power divided by apparent power. So, and just a reminder, the reactive power is neither consumed in the circuit nor it does any useful work. It merely flows back and forth in both directions in the circuit. It can't be measured by our altimeter. So that is just useless power in a circuit. So let's look at disadvantages of low power factor. And before we look at the disadvantages of low power factor, it is important that we first visualize power in terms of the current demand of a line. So for example, for the total power consumed by an AC circuit, it simply depends upon one, for a single phase circuit, you can say that power is defined by voltage, that is the line voltage multiplied by the line current cos phi, and in that we can determine the value of the line current by making the line current the subject, and in so doing this one will give you the amount of current specific for that single phase line. And it also power consumed in an AC circuit depends on if the circuit is three-phase supply, whereby current in a three-phase supply is given by power divided by √3 multiplied by the line voltage cos phi. So with those two in mind, then a low power factor leads to the following. A low power factor leads to the following. 1. It leads to large kVA rating of equipments. This is simply the rating of equipments such as alternators, transformers, switch gears being rated at a very high value, and that high value, it has some impact on the the cost implication. It has some impact on the cost implication. So we simply say that kVA rating of equipment is always inversely proportional to the power factor. Inversely proportional to the power factor. At a low PF, the kVA ratings of equipment has to be made very large, and this makes the equipment to become larger and expensive. It makes the equipment to become larger and very expensive. Then the other factor is touching on the current, the supply current, and with the supply current, it makes the size of the conductor to increase. It makes the size of the conductor to increase. So we have a greater conductor size, and you can simply say the size of the conductor always depend upon the magnitude of the current in that line or in that circuit, and therefore to transmit or distribute the same power at a low power factor, the conductor has to carry more current, which increases the size of the conductor, and this again makes the system very expensive. So we are simply saying to transmit or distribute a fixed amount of power at a constant voltage, the conductor will have to carry more current at a very low power factor, and this necessitates large conductor sizes. Then the other disadvantage is also again touching on the current. So we have large copper losses along the transmission stroke consumption stroke distribution. So we have large copper losses, and the losses in the system are proportional to the square of the current. So at a very low PF, will cause an increase in current, which results in more losses, and this reduces the efficiency of the system. Then the other disadvantage is there will be poor voltage regulation. regulation. So you can simply say that low lag in power factor results in large current, which causes greater voltage drops, in generators, transformers, and distribution lines stroke transmission lines, which leads to poor voltage regulation. And in order to keep the voltage regulation within permissible limits, it implies that you add extra equipments such as voltage regulators, and the addition of voltage regulators again makes the system complex and very expensive. And it is because now the voltage regulators come at a cost, then they come at complicating the design and so on. Then it reduces handling capacity of the system. So the lag in power factor reduces the handling capacity of all the elements in the system, and that is because the reactive component of the current prevents the full utilization of the installed capacities of the element. It prevents the full utilization of the installed capacities within the elements. And with those disadvantages, and again, if you look, the disadvantages are very costly, they are also very key. So I would like, if we consider, we look at advantages of now improving power factor, and these advantages are simply basing on redoing the disadvantage of low power factor. So from that discussion there, we've seen that if power system works with a low power factor, the capital cost of the system in generation, transmission, and distribution increases. So therefore, it is advantageous for both consumers and suppliers to work at high improved power factor. It is advantageous for both consumers and suppliers to work at higher improved power factor, and these are the reason why you need to work at an high improved power factor, or the advantages of improving power factor. One, if you look at the active power capacity of the prime mover will be better utilized. That is to say, the active capacity of the prime mover will be better utilized. Then the other advantage is the apparent capacity of the alternators, transformers, and distribution line is also increased. Then the other advantage, number 3, is there is reduction in transmission line losses. As you had seen here, we had said that in disadvantage number 3, there's large copper losses. Now with an improved power factor, it undoes that, and it leads to reduction in the power, that is reduction in transmission line losses by making the transmitting current to be very small in terms of the magnitude. So that leads to very small losses. Then the voltage regulation is improved by having minimum voltage drops in the transmission line. So you can simply say the voltage drop in the transmission line decreases, which results in a better voltage regulation. Then the other advantage is the efficiency of every plant is increased. That is, the efficiency of every generating station increases. And the other advantage is the overall cost per unit decreases. The overall cost per unit decreases. That is, in terms of costing of electricity. If you at your own home you have a better improved power factor, then you realize that the billing of electricity goes down. So maybe in a quick way we can remind ourselves the advantages of an improved power factor. And one, we said the active capacity of the prime mover is better utilized. Then number two, we have said the apparent capacity of alternators, transformers, and the transmission lines is increased. Then number three, we have said there is reduction in transmission line losses because you are transmitting at a very small current. Then number four, we have said the voltage drops in the transmission line decreases, which results in a better voltage regulation. Then number four, there is increase in efficiency of power generating plants. Increase in efficiency of power generating plants. Then the last advantage we have said there is decrease in the overall cost of electricity per units. So there is overall cost per unit decreases. So then the other thing is the causes of a low power factor. The causes of a low power factor. So we have cause number one, or the main cause of a low power factor, is that we find that in most of the industries we have our AC motors being induction type. So it can either be a single phase or a three-phase induction type motor, and all those kind of induction type motors, we've said that they operate at a low lagging power factor. They operate at a very low lagging power factor. Then the other cause of a low power factor, we have the transformers at substation having a lagging power factor. The transformers at our substations having a lagging power factor. Then the other cause number three is the heating furnace or induction in industries has a very low lagging power factor. The heating furnace, into bracket the arc or the induction of industries, has a very low power factor. Then cause number four, we have the arc lamps, electric discharge lamps, and industrial heating elements operating at a low lagging power factor. Then the other cause of a low power factor is is the varying load or the change in load. You find that in most cases we have the load in a power system is not constant, it keeps changing. So whereby in the morning and evening hours, we have high power consumption. And the reason why you're having high power consumption is because morning and evening hours, those are the peak hours, and most of us are at our homes, and in that home you can't stay in darkness, so you have to switch on your lamp. If you have a radio, you have to switch it on. You switch on your TV, and that mostly runs in the morning. It runs from 4 a.m. to around 8 a.m. in the morning, and in the evening it is from 5 p.m. to around 10 p.m. at night. And during the low load peak periods, during the low load periods, you find that the supply voltage is increased, and this increases the magnetization current, and this magnetization current results in decreased power factor. So you can say at a time when we are experiencing a low load periods, that is lunch hours, night hours, the supply voltage increases, which causes increase in the magnetization current, and hence the power factor of the system comes down. And just to be curious, you may research and I determine at you have different types of load, so you may determine the power factor at which they operate at. For example, you can talk of an arc lamp, and that are used in cinemas, and those ones operate at PF ranging from 0.3 to 0.7. We have the neon lamps and the signs. They operate at 0.4 to 0.5. We have the fluorescent lamps. They operate between a range of 0.6 to 0.8 power factor. Then we have the resistance heater, that's operated at a unit power factor. We have the induction furnace or the induction element, it operates at 0.6. We have the arc elements, they operate between 0.3 to 0.4. Then we have our induction motor, and most of the induction motors operate at a PF of 0.8, and that is lagging PF of 0.8. So having discussed the causes, we move on to the methods of improving power factor. So when we talk of methods of improving power factor, we are simply referring to the techniques and the technologies that we may employ to ensure that our power factor remains at unit, to ensure that our power factor is not costing us a lot of money, and to ensure that our electrical equipments are well safeguarded. So improving power factor means reducing the phase difference between voltage and current. It simply means reducing the phase voltage between voltage and current, and therefore Low PF is mainly associated to the fact that most loads are inductive and they take lagging currents. So most loads are inductive and hence they take lagging currents. So to improve this condition, some devices taking leading power are connected in parallel. They are connected in parallel with the load, e.g. a capacitor. And with the capacitor, what it does, it takes leading current, it draws a leading current and partially neutralizes the lagging reactive component of the load. It partially neutralizes, so it can either partially neutralize or it neutralize completely the lagging reactive components of the load current. And since the majority of our loads are inductive in nature, they require some amount of reactive power for them to function. They require some amount of reactive power for them to function. So on our methods, we have method number one, where it is referred to as the static capacitor or the capacitor bank method. Static capacitor or the capacitor bank method. And in this method, power factor is improved by connecting a static capacitor in parallel with the equipment operating at lagging power factor. So in this method, I have said PF is improved by connecting a static capacitor in parallel with the equipment operating at lagging power factor. And what does this capacitor do? Yeah, I have said that the capacitor draws leading current from the supply voltage at 90 degrees and it compensates for the lagging reactive component of the load current. So it draws leading current from the supply voltage at 90 degrees or by 90 degrees and compensates for the lagging reactive component of the load current. So that compensating simply implies it neutralizes the lagging reactive component of the load current, hence improving the power factor of the load, So this one can be used in three-phase. It can be used in three-phase, either in star or delta connection. It's much applicable for three-phase, either in delta or the star connection, as shown below. So if you look keenly, the first one here is a star connected capacitor bank, and it is improving the power factor of our three-phase load here. So this one, in most cases, it can be a three-phase induction motor. So it has to be, the power factor has to be made close to a unit, that is close to 1. And on this other side we have a delta connection, and again it is working to improve the PF of our three-phase load, which in this case can be a three-phase induction motor. It can be a three-phase induction motor. So what are some of the advantages of this method, or what are some of the gains from this method? So one, we have reduced losses. And the losses can be termed as less than 0.5. So the losses of power are reduced, and in overall they can be termed at 0.5%. Then advantage number two, it requires very little maintenance since there are no rotating parts. So it requires very little maintenance since there are no rotating parts. Then advantage number two, it has high efficiency. Above 99%. Then there is low initial cost. That is, the installing cost is very low. Then the other advantage is easy to install, since it has a very small weight, or it is light in weight, so that makes it very easy to install. It can be easily installed as they are light in weight. Then the other advantage is it does not require any foundation. So in other words, it does not require any support for it to be installed. It does not require any foundation stroke support for it to be installed. Then it has its shortcomings, or the disadvantages, and one of the disadvantages, it has a very short service life. That is a very short lifespan. It ranges from 8 to 10 years maximally. Then in cases of overvoltage, it can be easily damaged if your line experiences an overvoltage, maybe from lightning and so on, or fluctuations that increases the voltage of the line. So that one leads to automatic damaging of the static capacitors. Then its repair is uneconomical. Once it is damaged, it is very uneconomical to do a repair. It's very uneconomical to do a repair once they are damaged. Then the other method 2, is by use of synchronous condenser. And a synchronous condenser is simply an overexcited synchronous motor that is running at no load. An overexcited synchronous motor that is running at no load. And this motor is simply connected to your three-phase supply, and what it does, is it takes leading current, and this makes it to behave like a capacitor when connected across a supply. And the leading current that is drawn by this synchronous motor partially or fully neutralizes the lagging reactive component of the load current, thereby improving power factor. So the overexcited synchronous motor takes a leading current and behaves like a capacitor. When it is connected across a supply, it draws leading current that partially or completely neutralizes the lagging reactive component of the load current, thereby improving the power factor. And it is shown here. So on this side we have our three-phase supply. Then in between the three-phase supply and the load and the three-phase load is whereby we connect our three-phase synchronous motor, and in this case it is referred to as a three-phase synchronous condenser, because once it is connected in this form it will automatically behave like a capacitor. And if you can look here, we have a current IM that is being supplied to this synchronous motor, and after that we have another current IL, that is the load current. So that means it simply implies that from our phasor diagram here, if you look at keenly, we have a current IM and a voltage V, and that is simply our initial voltage and current. Then we have another current I and another current IL. This is the load current, and IM is simply the current to our synchronous motor. Then from that phasor diagram, we can simply note that the three-phase load takes current IL at a lagging power factor, and that is cos phi L. And in this case our cos phi L is phi 2. This is our phi 2 here. Therefore, the other thing that we can note is the synchronous condenser takes a current IM that is on top there, which leads the voltage by an angle phi m. So the current to our synchronous condenser leads the voltage V by an angle phi m. Then the other thing is the resultant current I is in phase, is the phase sum of IM and IL. So current I is equals to IM current I is equals to our current Im. It is the phasor sum of Im plus the phasor current IL. So again, keep in mind that current I, this is the supply current, is our supply current from the three phase, and Im is the current to the motor, that is the synchronous condenser or the three phase synchronous motor. And now this is the current to our three phase load. So current I comprises of Im and IL. Therefore, it is clear that angle phi, the angle between voltage and current, this angle here, is less than the phi 2 here, that is IL, that is phi L or phi 2 here, and hence cos phi, the cos of this angle, that is the angle between voltage and current, the cos of this angle is greater than the cos of phi 2. So you can simply say that cos phi is greater than cos phi 2. So this increases, so that therefore this implies that our power factor increases from phi 2 to cos phi. It increases from cos phi 2 to cos phi, and therefore our power factor is improved. Therefore, this kind of improving method is mainly used in industrial plants or large utility system, and that is at a major, maybe a utility system can be a busy and bulky substation. So it is mainly appropriate for bulky substations, and it has the following advantages. One, by varying the field excitation of the synchronous motor, or the synchronous condenser, the power factor can be improved to a desired value. The power factor can be improved to a desired value or a final value. Then advantage number two is that the motor windings have high thermal stability to short circuit current. The motor windings have high thermal stability to short circuit current. So, and that implies that they can withstand overloading. They can withstand overloading. Then the other advantage is faults. In case of a fault, they can be easily removed or troubleshooted. Faults can be easily diagnosed, removed, and troubleshooted. Then it has several demerits, and one of the demerit is the cost is high compared to static capacitor of the same size above 500 kVAs. 500 kVAs. So it simply implies that this one is more expensive compared to static capacitors, except for sizes above 500 kVAs. Then the other disadvantage is maintenance and operating cost is high. Then there is considerable losses in rotating parts of the synchronous condenser. There is considerable losses in the rotating parts of the synchronous condenser. Then we have low efficiency compared to static capacitors. Remember, we said that a static capacitor have an efficiency of up to 99%. So this one has a low efficiency compared to static capacitor. Then there is production of noise as the synchronous motor is rotating. It produces some noise. The noise can be from the bearings, and the noise can be from the bearings. Then there is other disadvantage is it requires an auxiliary component or equipment for starting, and that is to say they require an auxiliary component since they are not self-starting. So the synchronous motor is not self-starting, hence it requires auxiliary equipment for starting. Then the other disadvantage is there are high chances of the synchronous condenser falling out of synchronism. High chances of the synchronous condenser falling out of synchronism, which leads to interruption of supply. So there are chances to fall synchronous condenser out of synchronism, which leads to interruption of supply. So having discussed that, we have looked at two methods of improving power factor. We have some other methods, and we have one which is very necessary, and we'll look at it in our next class. So have a wonderful time. Share the video, comment, like, and remember to subscribe. This is your channel for all your educational needs. Subscribe, share with your friends, comment, ask any question at the comment section, seek for any clarification, and in our next discussion we'll start from the third method, that is the phase advancers. Then from the first advances, we'll do some bit of calculations. We'll solve some numerical values. So keep in touch, subscribe, share, and comment. Wish you well. Wish you well. Thank you for being my audience.